Hello, so it's Dr. Daystorms again, and in this video we really are continuing on from what we've done in the previous videos on this chapter. And so if you haven't done so already, you will definitely want to watch the other videos concerning electrophilic aromatic substitution reactions. So for this video, we're going to go look at specific examples and try to explain the reasons why something would be OP versus M directing and why it would be activating versus deactivating. So how can you just look at an R group that's hanging off a benzene ring and at least have a good estimation on whether it's going to be activating an OP or M and deactivating. Okay, and when we say activating, it means its reaction would be faster than just regular benzene would, or deactivating means it would occur slower. All right, so let's just look at a very specific example to start things off with, and that's phenol. And so I'm going to draw phenol. Remember, that's a benzene ring that has an OH group hanging off of it. This time, you may not be able to see it very well, but I'm going to put in the lone pair electrons. And then we have our generic EY. And just for clarity's sake, I'm going to do it as a para position. But remember, phenol is OP directing. So the major products in this type of electrophilic aromatic substitution will be in the O position or the P position. Okay. So I'm just going to draw it down here to make it a little easier for me to draw everything in for clarity's sake. So the first step is the benzene ring when the double bonds from it's going to swing out, boom, sound effects optional, to attack the E, because remember E is delta plus, the Y is more electronegative, delta minus, and the Y leaves. Okay, so let's draw the intermediate. Remember there were resonance structures that were possible. So we have the benzene ring, or what had been the benzene ring, this double bond, O with its lone pair electrons, two sets of lone pair electrons, even though they're not showing up very well. Sorry, I've run out of blackboard room on here. And remember, there still is a hydrogen that on the carbon that the electrophile is attached to, and then technically we do have a Y minus. Okay. But we have a carbocation. The carbocation is located 2 positions away from the carbon that has the alcohol group on it. Okay, so now let's do our possible resonance structures for this intermediate. We can swing this down, boom. We can draw it. So let's draw what we have. The E is still there. There's a double bond. OH. Okay. We have a double bond here. And now we have the carbocation, which is on the carbon that the OH is hanging off of. Which at first you may think, oh, well, the oxygen, though, is so electronegative that would destabilize it. However, it doesn't. It doesn't because of this reason. I'm going to actually switch colors here to try to see if it'll be a little bit more obvious. What we can do here is we actually have another possible resonance structure. We have, I should say, 2 more possible resonance structures. So starting from this second resonance structure, we can take 2 of the lone electrons of the oxygen. Boom. They can go and smack that carbocation. So let's draw what that looks like. I'm going to do it down here. And in doing so, it's going to look like follows. The E is still there. Double bond, double bond. Okay, and now the positive charge is actually located on the oxygen. Yes, the oxygen is not the happiest in the world, but it's still possible. In fact, at certain pHs, when it loses that, if it loses that hydrogen, then it's actually will be neutral, and it's actually happy. It's fine, and our body actually does reactions similar to this with things like the quinone. So for those of you who are biochemistry, we have similar reactions that occur with the quinones versus the quinol groups. Okay, so that's possible. And then we also have another possible resonance structure. So I'm going to go back up here, and in a different color. Let me just choose a different color. We can have this double bond coming over to smacking it, boom, and in doing so, this resonance structure is also possible. So since we have, so the OH, whoops, that O did not come out well. The OH group, double bond, E, double bond, and the carbocation is located ortho to the E, meta to the oxygen. And so that's why we actually have 4 possible resonance structures here. Since there are more possible resonance structures, it makes it more stable than what you'd expect. I apologize for that. One of my dogs started to bark. But because there are even more resonance structures possible, it makes it more stable and definitely makes this an OP director. So this is OP directing, and it's highly or very strongly activating. Alright, so let's look at another example though. Okay, so this time, let's look at something like a carboxylic acid. So now we're doing benzoic acid. So for benzoic acid, the problem is, I'm just going to skip ahead and just draw the various, like if it was OP, this is going to be one of the possible resonance structures. Because so far what we've been seeing is any time that you have an OP director, you get a carbocation. Oh, can't get those to. Carbocation is located. So I'm just going to show it here as if it's on P. But if this was true, and it is not, this does not occur, and I'm going to show you the reason why it doesn't occur, is the carbocation is located right there. So the problem here is the fact that the atom that is directly attached to the benzene ring, the one that would have to help out that carbocation to make it activating and to make it OP, it does not have any lone pair electrons. In fact, it's not like a methyl group where it has extra electron density it can loan. The reason being is that the oxygens that are attached to the carbons directly attached are pulling all the electron density away. So because of that, this carbon right here is even more delta plus than what you'd expect. And since it's already delta plus, it cannot help that out. So how can someone tell if something is OP versus M? So it's going to be an OP directing if the atom directly attached has lone pair electrons. Okay. Now, or it's some type of alkyl group that can alkane, alkene. Okay. Now it's M if if the atom directly attached, let's say for example, is a carbon that links to a more electronegative atom. And remember in class I abbreviate electronegative as EN, atom. So what do I mean by these? What are some of the examples here? Okay, so I'm going to use a different color to write out the examples. So for example, in this top one we could have things like even something like this, to where this is a, some type of ester group. And the reason why is even though it's not the best, it's going to be OP directing and activating, but it's not as strongly activating as the oxygen by itself. And that's because this oxygen right here is the one that's directly attached, and it does have lone pair electrons that it can lend. Okay? So that would be an OP director. Okay, so what are some of the other examples that we could have? Let me replace the P because OP. We could have something that is an OP director and activating is anything that's a nitrogen that's directly attached. So if you have a nitrogen, I'm just going to do it this way. And the reason being is because the nitrogen has lone pair electrons. Right? So those are going to be OP directors. If there's a nitrogen that's directly attached or an oxygen that's directly attached, even if there's something else that's attached to that nitrogen or the oxygen, it's going to be OP directing and it's going to be activating. Now, if it's an amino group or an alcohol group, it's very strongly activating, whereas it's just activating if it's, like an amide or an ester group that's directly attached, where the oxygen is the one that's the linking group. Okay? And then the other option is for if it's an alkyl, which what we mean by that is, once again, any type of alkyl group. So whether it's something that looks like this, even. So an alkenyl group would be activating and would be OP. Or it could even be like an alkyne. Okay. Or like some type of, methyl, ethyl, propyl, butyl, any of those type of groups would be OP activating. Now we're going to talk about one exception to this rule in just a moment. Whereas here, for the M directors, I'm going to go ahead and just give myself a little bit more room. Remember, we're talking about it's going to be M directing if it's a carbon that's directly attached to the benzene. So this time I'm going to draw the benzene ring out so that way you can see. So this is the benzene ring. Right? And let's draw what we mean. So we have a carbon, but if that carbon is attached to something else that's more electronegative, so for example, an aldehyde, since it's attached to this oxygen, it's going to make it an M director and deactivating. What about if it's a cyanide? Okay. So once again, the nitrogen's more electronegative, so it's going to be deactivating and it's going to be an M director. Okay. If it's this kind, whoops, because before, remember I said if it was an amide linkage, then it was going to be, whoops, OP. However, it's only an OP director if it's the nitrogen that's linking atom. When it's the carbon, it's going to be a meta director because that carbon doesn't have lone pair electrons and that carbon is directly attached to other more electronegative atoms. So this one is also going to be an M director and deactivating. Other things that can be deactivating in M is a sulfonyl group. So it's not a carbon. This is what that looks like. So you can see, hopefully you can see where when there's a negative charge. Oh, I cannot draw my negatives in here. It's not working very well. There'd be a negative charge on this oxygen. But the sulfonyl group was going to be meta-directing and deactivating. The reason being is that sulfur doesn't have lone pair electrons to help it out, and that sulfur is attached to more electronegative atoms, like the oxygens. Okay? And one other one that actually you're going to see, and it's very deactivating, is the nitrosyl group. So the NO2 group, the nitro group, and that's because, once again, is if you draw out the Lewis structure, it looks like this. So normally, we'd say, oh, it's a nitrogen because it's directly attached. However, that nitrogen is attached to oxygens, and the nitrogen itself even has a positive charge, and the oxygens share a negative charge to resonance. And so that's going to be strongly deactivating, and it's going to be a meta, because that nitrogen does not have lone pair electrons to help it out. Okay, so remember I said that there was an exception. This is the exception. What if we have, let me switch back to yellow. What if we have this, a halogen? So halogens have lone pair electrons. So believe it or not, they're going to be OP directors. However, they are the exception in the fact that they're OP, but they're deactivating. They're actually slower than what you would expect. And that's because they're deactivating, because what happens is if we draw, I'm just going to draw one. You can look at all of the resonance structures yourself. But if we draw the one, so for example, if it was the P, this is what one of the intermediates resonance structures would look like. It does happen, but it's not happy. So you can imagine a fluorine having a positive charge is not happy, and so because of that, it's going to be OP, but it's going to be deactivating. All the other OP directing groups are activating, right? So let's just work some examples of doing, like what happens, like how to pick what the major products are going to be. Okay, so here I have an example. This is a methylated benzaldehyde. Okay, and so I have an example of doing a sulfonyl reaction. So you can see here we've got sulfuric acid and heat, so we're adding a sulfonyl group. Now the question is, what will be the major product here? So the way that I do it is just look and write out what each of the substituents is. And so you may want to pause this on your own, try to figure it out, and then see if you're correct. So we first look at the methyl group, and it's an OP director. And so in this color, that means it's going to either go here, here, or here. Whereas in a different color, we're going to look at the aldehyde. Aldehydes are meta directors. There and there. Okay, so in this example, you would have to say, so which one predominates? Now, I picked this for a couple of reasons. One is sometimes you'll find out that the positions would match up, but this one doesn't. We have a deactivating M with the formyl group, this aldehyde, and we have an activating OP from the methyl group. So how do you know which one predominates? The one that predominates in this example here is going to be the one that is more activating. So the more activating group predicts regioselectivity. And so it predicts the regioselectivity. Now we have, so that means it's going to be the OP. So of the three possible OP ones, we're adding this large sulfonyl group to it. So which of these three positions is most likely going to be the best of the three? So let's just start to use some logic here. If it goes to this position right there, you're trying to stick a large sulfonyl group between a methyl group and an aldehyde. It's going to feel crowded. Remember, that's called steric hindrance. So most likely, that's not the best position. Okay. Likewise, if it goes here, we're going to be next door to the aldehyde, which takes up more room than the methyl group. So chances are the best position is going to be that, the one that's ortho to the OP, and the furthest away from the largest group. Okay, so let's just draw what that looks like. Let me go back to this other color. Of course, ultimately, I'm just going to draw the final product. The aldehyde is still there. The methyl group is still there. But now we've added on the sulfonyl group. Okay, which I'm just going to draw it this way instead of drawing it all the way out. And so that would be the major product. So let's do another example. Okay, so in this example, we have this di-substituted benzene ring, and we're doing a bromination reaction. And so just to remind yourself that with the bromination reaction of the benzene ring, when you're wanting the bromine group or the halogen group to be added directly to the benzene ring, you have to use iron bromide or iron chloride, iron 3 bromide or iron 3 chloride in order for the reaction to occur. That's the catalyst. So now we have to figure out what position or positions, if we're doing a monobromination reaction, what will they be? So if we look at the first one, let's look at this amide over here. Since it's an amide, it's directly attached, the carbon's one that's directly attached. However, that carbon has more electronegative things hanging off of it. And so it's a meta-director. And it's deactivating. Okay? Then if we look, so the positions for it, we go to meta, so it's going to be here or here. Now, let's pick a different color. For the amino group, since it's going to have lone pair electrons, it's going to be an OP and it's activating. So the OP, well, we can't do the P position because there's something already there. So that one's out. And then this is the O positions there. In this instance, the positions actually line up and they are the same. So, assuming that we just have a monohalogenation event, this is what our final product, the major final product would be. Whoops, my circle got off. So we still have an amino group. We still have the amide. But now we have a bromine. And it doesn't really matter which of the O positions because it's the same compound regardless. But there would be the bromine. Okay, so on your own you may want to just work as many of these examples out as you possibly can. And that until you feel more comfortable, feel free to come by and see me during office hours or set up an appointment and we can go and work through some of the suggested problems or other examples together. I'll see you in class.